Chapter 11 is concerned with analyzing a categorical variable versus a metric variable. And you recall that when Chapter 10, regression analysis, is about one metric variable versus another metric variable. Well, in this case, we're going to change the independent variable to a categorical variable. And so we'll see all that unfold here. But it's called analysis of variance, and the acronym for it is ANOVA. So this, my understanding of the history of this is that it was developed in the 1920s. Seed companies were developing different hybrids of crops, and they wanted to have a good statistical way of analyzing the performance of these different hybrids. And so suppose we have these hybrids of corn, soy, whatever you want to call it, wheat. Let's see, suppose this is the yield axis. So this could be, yield could be in bushels per acre of corn or whatever it is they're growing. And suppose we have a hybrid A, hybrid B, hybrid C, hybrid D, and so on. I'll list 5 of them here. So here are 5 hybrids, and they're under scientific conditions. They're planted in pretty much the same soil, the same watering conditions, the same sunlight conditions. Everything is controlled for. When we say controlled for in statistics, that means that when you control a variable, that means that everything you're studying has the same value for that variable. In other words, it's not changing. Because obviously if you gave hybrid A more water than hybrid D, then it may grow better. And so if you keep the amount of water controlled, that means they get the same amount of water. So by controlling all the variables possible, the only thing left that could cause a variation in yield or output would be either the hybrid or some kind of random factors. There's still some randomness to all this. But anyway, here was their question. That, okay, so we have these hybrids. We can't put numbers on hybrids in the sense that of a metric variable. There's nothing statistical about A, B, C, D, and E that we can calculate with. However, in this case, you can measure the yield per acre, bushels per acre. And so here is the categorical variable on the independent axis, and the vertical dependent axis is the metric variable. So they go out, and after the end of the growing season, they harvest the crops and measure all these yields. So the question became, well, how do we know what is truly the best hybrid? For example, here hybrid C has the highest yield, but how do we know that's not just due to randomness, that truly is a variation that is significant? So in other words, how can we measure the significance of these differences we're seeing to see if they truly are statistically significant or if it's just due to randomness? So there we go. Out of that became the analysis of variance. Now when you think about it, a uniform distribution is a distribution in which you expect all the categorical variables to have the same amount. For example, if and I may have used this way back in another video. Suppose we went out in a parking lot and wrote down the last numerical digit on every license plate. All right, sounds kind of boring to me, but until you look at the numbers, then I think it's kind of exciting. But you go out and you write down the last digit of every person's license plate. All right, what do you expect to see? Well, you would expect that you would have an equal number of zeros, ones, twos, threes, fours, and fives, all the way up to 9. And so that would be uniformly distributed. If that's true, you expect the same number of last digits, because you're thinking, well, they're just randomly distributed. The digits 0 through 9 are randomly distributed, and so they're uniformly distributed. I'm sorry, they're randomly distributed to the population. However, when we sample it, we expect that the distribution is uniform and about the same for each number. Now, are we always going to get the same uniform amount? Of course not. So one day you might find 20 cars with this digit and 22 with that, and 19 with that. And so we expect some random variation there. And likewise, we expect some random variation if there's no difference in yield capabilities for the hybrids, if there's no difference. However, we will see some differences, and then the question becomes, when do these differences become important enough or statistically exaggerated enough to really mean something? So that's the essence of analysis of variance. The textbook gives a definition for it on page 475. It says, analysis of variance is a statistical method used for the comparison of the means of a different variable across different groups. And so we're going to think of these as groups. This categorical variable is divided into groups. And well, I think the authors of the textbook started this with a great example. And it begins around page 476. And it reads this. There's tables there on page 476 and 77. Violent crimes in the contiguous 48 states in 1986. The contiguous 48 states would be everything but everybody but Hawaii and Alaska. So they wrote down the crime rate per 100,000 in the population. You know, if they wrote down what's the how many violent crimes were committed in each state, then New York, California would probably be number 1 and 2. One would. And but by saying crime rate per 100,000 in the population, that allows us to compare big states with small states like Wyoming or North Dakota. So the author took all these states, wrote down the crime rate per 100,000 in the population, and he grouped them together by region. So you see the first part of the table, you have Maine, New Hampshire, Vermont, Massachusetts, Rhode Island, Connecticut. That's called New England. The next 3 states, New York, New Jersey, and Pennsylvania, are Mid-Atlantic, and so on and so forth. So he's divided them up into 7 groups, 7 categories. And so the region of the country is by category. So let me do a little racing here, and I'll start talking more about this problem. I've taken the data from this problem on page 476, 477, and created a histogram. It's not the prettiest histogram I've ever done, but I'll read off the numbers here and the regions. This is the by region, and it's Mid-Atlantic, Midwest, New England, Pacific Coast, Rocky Mountain, South, and Southwest was the last one. So I used the same order that the author used, and I guess he went with alphabetical order. Okay, he put them in alphabetical order. And looking at these states, I calculated all the averages for each state, the means for each state. And so the mean crime rate for the Mid-Atlantic states was 639, which happens to be the highest. 639 per 1,000. And then Midwest was 375 per 100,000. New England was 293 for every 100,000. That happens to be the lowest. Pacific Coast was 636, almost tied with Mid-Atlantic. And then Rocky Mountain was 364. The South was 526, and the Southwest was 620. And so it looks like Mid-Atlantic, Pacific Coast, and Southwest are pretty well tied for first. And New England is way down the list there. So I've been to all these regions of the country, and I can tell you that probably the reason North Dakota's is so small, they had the smallest crime rate that year, 51 violent crimes per 100,000 people in the population. My guess in North Dakota is why it's so low, because no one lives there. There's hardly anybody there in North Dakota. So how can you have crimes if no one's there? So anyway, if you want to see a crime in North Dakota, watch the movie Fargo. Okay, the highest crime rate is my home state of Florida, 1,036. And so I grew up in Florida, and my theory on this for 1986, and no, I was not in Florida in 1986, I was in California, is that was probably the year, one of the years that Castro emptied his prisons of all his hardened criminals and insane people and so forth. He kind of unloaded the prisons, and maybe that was the year they came over to Florida and created a lot of havoc. So I don't know if that's the explanation, but it's my theory. All right, so if you look here, the crime rates by state vary from a low of 51 in North Dakota to over 1,000 in Florida. And these are the averages. And so the question becomes, does the region of the country have some kind of relationship to the violent crime rate? All right, do we expect to find more violent crime in certain regions of the country? And you know, this doesn't begin to answer the question why, if that's really true, but we need a way to analyze this to see, well, is there a relationship here? And the relationship factor that can be calculated is called capital R. And so capital R, and please capitalize it for this chapter, analysis of variance, it measures a type of, it's a numerical measure of relationship between categorical variable and the metric variable. And R lives between 0 and 1. So it's a positive number. And as you might suspect, it's closely related to the correlation coefficient in regression analysis. Remember, the correlation coefficient, small case r, live between -1 and 1. That's because we can have negative correlations and positive correlations. And in this case, there's no such thing as a negative correlation here. And so that's out the window. There's no negativeness to this analysis. It's just the question is there a relationship? And so please don't use the word correlation in this chapter. It doesn't fit. Correlation is associated with regression analysis, not analysis of variance. So we measure a relationship number, coefficient, R, and that's the basis on which we will formulate some kind of hypothesis test, thinking, to determine is there a real relationship here, or is it just due to randomness? So is this just all smokescreen? Is it really true that there's a relationship between violent crime in the region of the country, or is that just due to random factors? So that's what analysis of variance seeks to answer. Now, in looking through the book here, on page 478, he did a scatter plot of all the states by groups, by regions, the category region. And so you see 3 scatter plot dots for Mid-Atlantic, and so on. And so there's sort of a visual idea of what's going on. It's a little hard to look at that and tell, I think, is there really a relationship here that's significant or not. A little easier to see is on page 480. He's done a box plot, box plots, and I really haven't talked about box plots in these videos. A box plot indicates a bottom quartile, a second quartile, third and fourth quartile. So it sort of divides the numerical data into 4 quartiles. And but the middle line segment of the box plot would be, I believe, the mean of the data. Well, anyway, if you turn over to page, but it's more visual. It's a little better visual, I think, on this data than the scatter plot of data. Now, if you turn over to page 482, he does go back to the scatter plot idea, and now he's calculated the mean for each of these categories. Well, that's what I did. And so if you take the his red segments here connecting all the means basically would be the same if you connected the tops of these bars together. You would have pretty much the same thing he's got. And so his scatter plot with those averages calculated in with a little red curve there, not a curve, it's various segments together, is quite a bit like the histogram I have here. Now he's got one other thing here. He has an average, and I believe the average for all the states was 460. And so if I draw a line here, 460 is the country's average, and that's going to be a significant thing to think about as well. All right, so how do we deal with all this? Okay, how do we deal with all this? So I'm going to erase the board and cover how the calculations are done for analysis and variance, and we'll fill out an analysis and variance table and do a hypothesis test with it.